let's do another proof. This is an interesting one. It's worth watching because there's a couple of sophisticated math tricks happening in here. There's more than one definition for E, and that is part of what comes into this actual proof here. Let's actually generalize this a little bit. Let's make this f of x equals, we'll use a b. I like b's. B to the x. A lot of books use an a here. So some base to an x. We'll see if we can find the derivative of this exponential style function, and then we'll look at what happens when we put an e in there. So we only got this definition. That's all we really have to work with. So if I write b minus b to the x all over h. There's a question of how do I actually do the composition. Make sure you get this x plus h in there correctly. It goes right inside of that exponent, x plus h. Little small there, sorry. Okay, so what could I possibly do with this? How could I possibly clean this up? And here's where a few exponent rules are going to come in. Clearly, we would need them to work with these exponents. So the limit as h goes to 0 of bx plus h. There's some other way of writing that. What was that? Oh yeah, that is b to the x times b to the h. Adding in the exponent is the same as multiplying on the outside. Very handy. Okay, maybe at this point you see what comes next. What could we possibly do? Usually there's factoring involved. Let's go ahead and factor. Okay, this b to the x comes all the way out. This is a limit with respect to h. H and x are totally independent. They have nothing to do with each other, so I can pull this b to the x all the way out of my limit. Thanks, limit laws. So I'm factoring it out of the top, I'm factoring it out of the fraction, I'm factoring it all the way out of the limit like my limit laws say I can. As far as h is concerned, b to the x is a constant. Okay, so what is left inside? If I pull out a b to the x from b to the x, it's a 1.
Welcome back. We are racing through this ability to take derivatives to find instantaneous rates of...
All right. So what happens if I pull out this b to the x from b to the x? I'm just left with a 1. Okay, so now I've got this b to the x function times something, whatever this limit is. And I don't know what this limit is right now, right? It's dependent on this b. Okay, so I'm going to do this really clever, almost devious math thing. You ready for this? We haven't really said what e is. So I'm going to do this clever thing here, and I'm going to say, all right, let's just define e, this number, to be exactly what I want it to be. The limit as h goes to 0 of e to the h minus 1, get that out of that exponent, e to the h minus 1 over h equals 1. Right? So this limit's going to depend on what this b is, and I'm just going to say, in the nicest possible case, it could be 1. And e is going to be the number that makes it that. This is such a weird thing the first time you see it. Okay, so let's back up a little bit here. Okay, so what is this limit as b to the h minus 1 over h? We're saying that the derivative of x is equal to itself, right? It's equal to f of x times this thing. Okay, whatever on earth this thing is, so some constant. And we kind of brought this up earlier, that having your derivative be yourself times a constant, that's nice. What is the nicest constant it could be? How about a 1? So it's going to be a different constant depending on what the base is. We'll see what it is in the future. It's going to involve a natural log. But in the case of e, it's going to be a 1. In fact, that is our definition of the number e. So what this means for us is that the derivative of e to the x is, well, e to the x times 1. And that's just e to the x. So clever. It means that our derivative for 2 to the x is going to be 2 to the x times some constant I don't know yet. And we'll figure out what that constant is really soon. It's going to be the natural log of 2. But we'll get there. All right. One more note on this before I leave it. Some of you may have seen another definition for e as a limit, possibly. A limit as n goes to infinity of 1 plus 1 over n to the n. So this number on the inside is going to 1, while this number on the outside is going to infinity. So numbers closer and closer to 1 to higher and higher powers, they balance out to reach the number e. This shows up if you're learning about e in terms of compound interest. This looks a lot like a compound interest formula. It turns out these two definitions are in fact the same. And maybe a little later I can get into showing that they are. It's not too hard to show that they are, but it's not super enlightening right now either. All right. Thank you so much. That's a quick proof of why the derivative of e to the x is e to the x, but it's also a definition for the number e and why it's so important. All right. Thank you so much.